What if the greatest obstacle to reaching Mars isn't distance, money, engineering, or even human biology? What if the universe itself has already placed a limit in front of us? A limit so fundamental that no amount of intelligence can negotiate with it. Imagine building the most powerful spacecraft ever conceived, carrying the brightest minds humanity has produced, only to discover that the laws of physics are not merely challenging your dream. They're quietly telling you that some journeys may never be completed. And according to ideas explained by physicist Leonard Susskind, the real question isn't whether we can reach Mars. It's whether reality allows us to. For generations, Mars has occupied a unique place in the human imagination. It shines above us as a tiny red point of light, close enough to inspire confidence, yet distant enough to remain mysterious. Ancient civilizations imagined gods and warriors living there. Modern scientists see frozen valleys, extinct volcanoes, and dry riverbeds that whisper of a warmer past. Engineers see launch windows, orbital mechanics, and habitat modules. Entrepreneurs speak of colonies, cities beneath domes, and a second home for civilization. At first glance, the journey seems surprisingly achievable. Mars is not another galaxy. It isn't even another star system. On average, it's about 140 million miles away. We have already landed robotic explorers on its surface. We've flown helicopters in its thin atmosphere. We've mapped its mountains and sampled its rocks. Compared to the unimaginable distances separating us from other stars, Mars almost feels like our cosmic neighbor. So why hasn't anyone gone? The obvious answers are familiar. Rockets are expensive. Space is dangerous. Human bodies deteriorate in microgravity. Cosmic radiation damages cells and DNA. Months of isolation strain the mind. Every kilogram launched from Earth costs enormous amounts of energy. Every system must work perfectly because there is no roadside assistance between planets. But these are engineering problems. Physics is something else entirely. Engineering asks how. Physics asks whether. That distinction changes everything. Leonard Susskind has spent decades exploring some of the deepest questions about reality. As one of the pioneers of string theory and a major contributor to modern ideas about black holes and quantum gravity, his work repeatedly reveals an uncomfortable truth. Nature is not obligated to satisfy human ambition. It doesn't care what we hope is possible. It only follows its own mathematical rules. One of those rules is so familiar that we rarely stop to appreciate how extraordinary it is. Nothing with mass can travel at the speed of light. That single sentence quietly shapes every dream of exploration humanity has ever imagined. Light races through empty space at approximately 300,000 kilometers every second. It's so fast that sunlight reaches Earth in just over 8 minutes. Yet Mars, depending on where it is in its orbit, lies anywhere from roughly 3 to 22 light minutes away. That means even a radio message, the fastest thing we know how to send, can take more than 20 minutes to arrive. If information itself cannot travel faster, neither can astronauts. This isn't simply because our rockets are too weak. It's because the structure of space-time itself says no. Einstein's relativity transformed our understanding of motion forever. As an object accelerates toward the speed of light, something astonishing happens. Its energy requirements don't increase steadily. They explode. Every additional fraction of speed becomes dramatically more expensive than the last. To reach exactly the speed of light, an object with mass would require infinite energy. Not enormous energy, infinite energy. Infinity is nature's way of saying the destination isn't available. Imagine pushing a heavy boulder uphill. Every step requires more effort than the previous one. Now imagine the hill becoming infinitely steep. No matter how hard you push, the summit always retreats farther away. That's what relativity does to speed. The closer you approach light speed, the more stubborn reality becomes. For Mars, this doesn't prevent travel entirely. It simply guarantees that journeys remain painfully slow by human standards. Current missions require roughly 6 to 9 months. Future propulsion systems might reduce that dramatically. Nuclear thermal rockets could shorten the trip. Nuclear fusion, if mastered, might do even better. Some theoretical concepts, like antimatter engines, promise extraordinary performance. Yet even these remarkable technologies remain trapped beneath relativity's ceiling. Physics allows improvement. It forbids miracles. But speed is only the beginning of the story. Space itself is far less empty than our eyes suggest. Imagine leaving Earth's protective magnetic field. Suddenly, the invisible shield that quietly protects every living thing disappears behind you. Now, every second becomes an encounter with radiation born from exploding stars, violent solar eruptions, and distant galaxies. Cosmic rays are among the most energetic particles in the universe. Some travel for millions of years before striking a spacecraft. When they collide with human tissue, they don't merely bounce off. They shatter atoms. They damage DNA. They increase cancer risk. They may affect cognition in ways researchers are still trying to understand. Unlike movies, radiation isn't a dramatic explosion. It's a slow accumulation of invisible injuries. Shielding helps, but shielding creates another problem: mass. Every kilogram of protection requires more fuel. More fuel requires a larger rocket. A larger rocket requires even more fuel. This creates another unforgiving equation. The famous rocket equation, developed by Konstantin Tsiolkovsky, is one of the cruelest relationships in engineering. To carry more fuel, you need more fuel to carry that fuel. Imagine climbing a mountain while carrying extra food. The extra food makes your backpack heavier, forcing you to eat even more food during the climb, which requires carrying even more at the start. The mathematics quickly become brutal. This is why rockets launch with towering fuel tanks while the useful payload sitting on top appears surprisingly small. Most of what leaves Earth never reaches Mars. It becomes exhaust. Physics demands that enormous sacrifices be made simply to escape gravity, and gravity is another reminder that the universe never gives anything away for free. Every launch begins inside one of nature's deepest wells, Earth's gravity well. Leaving it requires extraordinary amounts of energy. Landing safely on Mars presents a different challenge entirely. Mars has enough atmosphere to create dangerous heating during entry, yet too little atmosphere to slow heavy spacecraft effectively. Engineers jokingly describe it as the worst of both worlds: too much atmosphere to ignore, too little to rely on. Landing a 1-ton robotic rover is difficult. Landing dozens of humans with habitats, life support systems, vehicles, food, and scientific equipment is a challenge of an entirely different scale. Yet perhaps the greatest surprise comes from something much smaller: time. We experience time as steady and reliable. Morning becomes afternoon, days become years. But Susskind often emphasizes that our everyday intuition fails us when physics becomes extreme. According to relativity, time itself is flexible. Move fast enough, and your clock slows relative to someone standing still. Approach intense gravity, and time slows again. These aren't philosophical ideas. They've been measured with astonishing precision. GPS satellites actually account for relativistic time shifts every single day. Without those corrections, your navigation system would drift by kilometers. Reality is already stranger than fiction. For a Mars mission, relativistic effects remain tiny, but they reveal something profound. Time is not universal. It depends on motion, it depends on gravity, it depends on geometry. The universe doesn't provide one master clock governing everything. Instead, each observer carries their own. This realization shattered centuries of assumptions. And once you've accepted that space and time themselves can bend, another question naturally emerges. Could we somehow bend space instead of racing through it? Science fiction loves this idea. Warp drives, hyperspace, faster than light travel. The dream appears elegant. Rather than moving the spacecraft faster than light, perhaps space itself could move. In 1994, physicist Miguel Alcubierre demonstrated that Einstein's equations mathematically permit a peculiar solution in which space contracts ahead of a spacecraft while expanding behind it. On paper, the ship remains locally stationary. Space does the moving. It sounds almost magical, but mathematics isn't engineering. The proposed solution requires forms of negative energy unlike anything humanity can produce in meaningful quantities. Quantum physics permits tiny negative energy effects under extremely restricted circumstances. But scaling those effects into a functioning warp drive appears overwhelmingly beyond anything currently understood. This distinction matters. The equations don't prove warp drives can be built. They merely show relativity doesn't instantly forbid certain geometries. Whether nature actually permits them remains unknown. Susskind has repeatedly urged caution. Whenever beautiful mathematics outruns experimental evidence, physics progresses through observation, not wishful thinking. The universe has a habit of humbling elegant ideas. That same humility appears in one of Suskind's most famous scientific battles. For decades, black holes presented a terrifying paradox. If information falling into a black hole vanished forever, quantum mechanics would be broken. Stephen Hawking initially argued that information truly disappeared. Susskind disagreed. The debate became one of the most important intellectual conflicts in modern physics. Eventually, growing evidence supported the idea that information survives, though encoded in extraordinarily subtle ways. The lesson extended beyond black holes. Reality often hides its deepest mechanisms beneath appearances. What looks impossible may conceal unexpected structure. What looks obvious may be profoundly wrong. Could Mars be another example? Perhaps the greatest barrier isn't propulsion. Perhaps it's understanding. Consider life support. A journey to Mars is not merely transportation, it's transporting an entire miniature Earth. Astronauts must carry breathable air, drinkable water, reliable electricity, food, medicine, spare parts, computers, communication systems, waste recycling, temperature control, psychological support, and protection from vacuum. Every one of these systems must survive for months without failure. On Earth, civilization quietly supports us every moment. Power grids, hospitals, factories, farmers, repair technicians. On a Mars spacecraft, civilization shrinks into a metal cylinder. Every bolt becomes existential. Every filter matters. Every software bug could become fatal. This isn't simply difficult. It's an extraordinary compression of everything that keeps humans alive. And then comes Mars itself. The planet welcomes no one. Average temperatures hover around minus 60 degrees Celsius. Atmospheric pressure is less than 1% of Earth's. Liquid water cannot persist for long on the surface. Dust storms can engulf the entire planet. The soil contains chemicals harmful to human biology. Nothing about Mars evolved for us. Every breath would be borrowed from machines. Every meal manufactured, every sunrise observed through layers of protective material separating fragile biology from lethal reality. Yet this is precisely why humanity remains fascinated. The impossible has always attracted explorers. Crossing oceans once seemed absurd. Flying across continents appeared impossible. Walking on the moon looked like fantasy. History teaches humility before declaring limits. Physics, however, teaches another kind of humility. Not every impossible thing eventually becomes possible. Some barriers truly are fundamental. No amount of innovation will create square circles. No technology will produce perpetual motion. No engineering can generate infinite energy. The challenge is discovering which dreams belong in which category. Mars occupies a fascinating middle ground. Physics does not forbid reaching it. Physics simply refuses to make it easy. But Suskind's work invites an even deeper reflection. Human beings often imagine themselves conquering nature, yet every scientific revolution tells the opposite story. Copernicus removed Earth from the center of the cosmos. Darwin revealed we are products of evolution. Einstein showed space and time are not absolute. Quantum mechanics demonstrated that certainty itself has limits. Again and again, reality asks humanity to replace comforting stories with stranger truths. Mars exploration continues that tradition. We don't travel there because physics promises success. We travel because understanding reality requires confronting it directly. Perhaps one day humans will stand inside lava tubes beneath the Martian surface, protected from radiation by ancient rock. Perhaps nuclear reactors will power underground habitats where children born on another world gaze at a tiny blue Earth hanging in a salmon-colored sky. Or perhaps the cost will remain too high. Perhaps robotic intelligence will outperform biological explorers. Perhaps autonomous machines will spread across the solar system while humanity remains largely earthbound. Neither outcome would represent failure. Both would reveal something about the universe we inhabit. Susskind often reminds students that physics isn't about telling us what we'd like to hear. It's about discovering what reality actually is. Sometimes that reality expands our imagination beyond anything fiction anticipated. Sometimes it narrows our dreams with uncompromising equations. The remarkable thing is that both outcomes are victories, because every genuine answer replaces illusion with understanding. The real frontier then may never have been Mars. It may be the invisible mathematical structure governing every atom in our bodies, every photon crossing interplanetary space, every second ticking inside our brains, and every law quietly deciding which futures remain forever unreachable. And if the universe has already written those limits into the fabric of space-time itself, then perhaps the greatest mystery isn't whether humanity will ever reach Mars. It's whether the deepest laws of reality are boundaries meant to imprison our ambitions, or invitations to discover that we have been asking the wrong question all along.